Right, I thought what I'd do this evening, since I have spent this week helping a student with MATLAB in my spare time, and because they're using Monte Carlo methods, and we're trying to do some parallelization of what they've done, and because I've not used parallel in MATLAB or done very much MATLAB at all, I thought I'd go through the routines that I used to use in the past to estimate pi with Monte Carlo methods rather than through direct numerical integration like the example that's in that repo I keep showing off. So, the other nice thing is I have a shiny new graphics tablet to try out, so I thought it'd be nice to try to do some annotation stuff and see how well it works. So what are we going to try and do? So, we know that the area of a circle is pi r squared. Okay, so if we draw a circle, it's a beautiful freehand circle, and we draw on an xy axis about 0. It's a circle of radius 1. Okay, what we want to do is, ignoring these 3 quadrants, we want to pick random xy coordinates between 0 and 1, see if they're inside the circle, and then the ratio of the points that are inside the circle to the total area of the square should be the area, right? And we're going to call that area A. Oops, I need to. Right, and A equals big A for, and of course that obviously means that A equals 4A. Right. So we have here is 4A equals pi r squared. R is 1, so it nearly falls out that 4A equals pi. So if we work out the area multiplied by 4, we should get the value of pi. Right, how do we start? Right, so here's MATLAB on my rocky machine. What we're going to demonstrate now is my complete inability to use the MATLAB GUI, because the only time I've interacted really with MATLAB is through the command line. I have used Octave a bit in the past for a course, but although they're similar, they're not the same. When I'm writing code, I like to write a library, right? And then I can call it, in this case, from the REPL in a fairly predictable way. So we'll call this function Monte Carlo pi .m. If we open that, I believe that's nice. MATLAB has given us some junk. I say junk. So like a skeleton of a function, right? It's one of the nice things about using an IDE, I suppose. I have to admit, even though I use them a lot. So I think what we want this function to take is we want 2 things out of this. We want the estimated value of pi and the amount of time it took, and then we want to put in the number of Monte Carlo samples, right? So in number of samples out pi, and then elapsed time. Okay, so if we do that, we'll call those the first things to return. I believe this is normally the name of the function, is it? And this will be, we'll call elapsed time. And the input arg should be number of samples. Right. So what are the steps? We're going to need a loop. Do the sampling. So for I equals 1 to number of samples, we probably need an accumulator. number in equals 0. What else? We wanted to do some timing. You can use timing in MATLAB with this thing called tick and tock. Say something like, say, start et equals tick. One of the things I really don't like about the MATLAB language is you can call functions by doing like no brackets if they have no arguments. That just, ugh. Right. I should say, like, I am not a big fan of the MATLAB language, but it is a very fast tool. Like, it used to be really slow, and they've really spent a lot of time at speeding it up. I think because what they used to do was, have all the functions the MATLAB calls written in MATLAB, which is like the clean language way of doing it, right? Because then you don't have to implement like a minimum number of things. But it did make it very slow, and I think that's probably one of the main reasons why Octave is so much slower, right? So Octave is an open source MATLAB re-implementation, but the performance is terrible. It's actually slower than R, which I think for me up until now held the candle as the slowest conceivable programming language. Right. So let's do this. So we've got some timing. So anyone who will get timing. We know that the return value we want to be 4 times the number that is in, right? From that thing we drew back here. It's a beautiful piece of artwork. So we want to say Monte Carlo pi 4 times number in. Right, I think at this point we could in fact execute this function. So why not I do that just to be very annoying? And I think the problem with using so many languages, you're like, which syntax is the way to do this? I think what we do is pi comma et equals Monte Carlo pi. Let's just do 100. And I think we should get back. No. There we go. Okay. So we get back our 2 values, right? My pi is currently 0. We're having a very short time because it's not doing any work. Right. So what we want to do is we want to do some sampling, right? Much in the same way that tick is a function you can call without brackets because that's how the language works. Rand generates a random number between 0 and 1, I think. Let's hope that I've done this right. So we want to say is x equals rand, y equals rand. Okay, so we've got 2 points x and y. Now the formula for a circle of radius 1 is that x squared plus y squared equals r squared, where r squared is 1. Right, so let's go back to this, to our digital blackboard. So, for a circle, which equals 1, right? So, how do we want to do this? We can do that test, right? So once we've got x and y, we get our random values. If they are on that line or under or less than that line, they are inside this bit here. And if they are more than 1, they are inside. They are outside. So if x squared plus y squared is less than or equal to 1, number, there's no plus equals in MATLAB. That was another thing I discovered when I was messing about equals number. Okay, so what it should now do is we should get random numbers. Okay, let's try that. So now if we run this, we get 3, 1, 2. What have we done wrong? Right. That does kind of look like pi, but the scale is off. What have we done wrong? Well, we have not done the ratio, have we? So we actually got the maths wrong. Right. So we've done a logical fail, because it's not the number in, it's the ratio that's in, right? Now we should get, I think, the right answer. There we go, 3.12. That's a really good estimate of pi, right, for 100 values. I did a Python repo a while back where I graphed the accuracy of 3 methods of estimating pi. One was this method, one was direct, was the normal method where you do the numerical integration, and there was a third one. I can't remember what I did for that. Oh, it was this, but not random. So like adding up on a grid just to see if it worked, right? And obviously this was by far and away the least accurate for the amount of effort way of estimating this, because it's a circle and it's actually a relatively simple line. If we had a very complicated line, then that might change, and it might become the stage where doing it experimentally like this is better than doing it analytically, performance-wise. Anyway, the point with most of these examples is to waste a lot of computer time, because we can then parallelize them later. Let's try this with a lot more. Okay, I think we can convince ourselves that as we increase the number, it gets a little bit better, but it's really tremendously rubbish. Okay, that's almost like a good value of pi. So what do we want to do now? So the student I was helping's code was serial, but not really serial. It calls a bunch of external functions. And those external functions at power forward are parallelized with power 4. But at this stage, I don't know anything about power 4. I have only programmed in other programming languages. So what I want to do is have a look at how power 4 behaves. Now, the obvious thing to do is just to see if MATLAB will let us do it. And that's replace power 4 with 4. This example is really simple, so it might just work. Let's see what happens. Now, the first thing it's going to do is it's going to try and start up a parallel pool, and that is an unbearably slow process, both on my laptop and on our HPC systems. I don't know why. I feel like it should just be threads and it should just be simple, but it's definitely starting up processes on our HPC systems. But first, a word from our sponsors, the Institutional VPN. Are you working from home? Perhaps your kids are off sick. Perhaps there's a global pandemic and going outside will literally kill you. Maybe a mop-headed buffoon has declared that everyone must remain indoors to protect the NHS while he hosts grand birthday parties for himself in his backyard. Or maybe it's a decade from now, and after the nuclear war, you spend a lot of your time hunting other humans through the nuclear wasteland for food and other resources. But the work of UCL goes on. The Institutional VPN creates a secure tunnel using the best encryption technology that Cisco can manage from your computer back to UCL's. This allows you to access services like MyHR, MyFinance, Myriad, and the Industrial Action Reporting Form from the comfort of your home, Starbucks, or underground nuclear bunker. You can obtain the Institutional VPN by going to the ISD website, selecting Get Connected, scrolling down and selecting Virtual Private Network. There you'll find instructions on how to install the client software on your Mac or PC, and sometimes even Linux. And having done so, you will shortly be connected to UCL's internal network and be able to do those fun things like filing expenses reports. The Institutional VPN, because the world might end, but nothing can stop University College London. Right, that's now run. You see it took 94 seconds. That is obviously an amazing speed up over the few seconds that it ran on a single processor, but that is largely because of the cost of starting up the parallel pool the first time. If we run it again, it should be a lot quicker. There we go, 4.8 seconds. Again, it's not really an improvement, but you know, as we increase the amount of work, that should scale out. So if we do 10. So that took 20 seconds, whereas the serial version hopefully would be longer. This is where it would be really nice if I work that out, wouldn't it? I'll just remove that just to be annoying. This is a terrible way of doing things, by the way. We should really have implemented a pure separate parallel and serial ones, but anyway.
So the common network together stuff back versus voice works. It's kind of still. Yeah, but like all the legal fees. I know because I have some big records on the I spend more on the paperwork and the essential money that kids eventually get back.
And there we go. So it took 39 seconds, right? Which is, so that shows it's not great scaling. We're getting twice speed up. I wonder, don't know how many threads it really thinks it's running on. Let's see let's put power 4 back in. Yeah, so I mucked about a bit more, but didn't really get much better performance out of it. I think there are a couple of possibilities really. One is I don't really know if rand is a thing which is to some degree synchronous, right? As in, it might be that because we are doing a call to a function and generally random numbers are not actually random, they're pseudo-random and they depend on the previous version. It might be that it's doing something odd there to synchronize threads and slowing down. I don't know. But yeah, that's slightly dissatisfying. But anyway, yes. So I've been playing around with MATLAB to try and get this user's code to work, and I did a shift version of this which is much closer to the behavior of their code, which does a bunch of slightly odd things with setting vectors and so forth. That's been fun. I don't think it's really changed my opinion on MATLAB, which is that it's very useful but not very nice to write code, which I think most people would agree. I think it's one of those applications that's really important for our systems because so many people use it, and it allows users to do things that they just couldn't do otherwise because they would need to learn to program. So, yes, we are not like most HPC centered. You can run MATLAB on our systems. You might have to mess about a bit to get parallel stuff to work nicely. And that's about it for this week.